Okay, so as I hope you've learned from your readings in the book and from your work out of the book, that you recognize that two-dimensional motion, projectile motion, is really just doubling your work. We're just taking everything we dealt with in terms of conceptualizing the motion, thinking about the players and thinking about what starts it and what ends it, and we've just added another dimension. So we're looking at all of those things horizontally, we're looking at all of those things vertically. Horizontal and vertical motion are completely independent of one another, which is so powerful because then we can analyze them independently and we can solve for the information that we're interested in for any given problem in projectile motion. So projectile motion, remember, is a form of free fall. So we are only having an influence of the motion in the vertical direction by gravity, and so that gives us some implied information right off the bat. And we're going to look at how problem solving looks in two dimensions. So we're going to show that doubling of work from one dimension to two dimensions. So we're going to use example 4.4 out of the Knight textbook, and it reads, a stuntman drives a car off a 10-meter high cliff at a speed of 20 meters per second. How far does the car land from the base of the cliff? So we're going to use this example. It's very straightforward projectile motion with a horizontal launch velocity as a way to understand how to do the process of problem solving. And then we'll use that problem solving process in some other examples with two-dimensional motion. Okay, so the first step of a two-dimensional motion problem solving is to identify the object. Some of these steps are going to look very familiar. In fact, they'll be identical, and we're going to double the amount of work you have to do for each of those steps. So what is the object in this situation? This car that's driving off a cliff. Well, the object's the car. That's the motion, the object that we're interested in analyzing the motion for. We also, as we've done in all of our problem solving, we also want to look at what defines the beginning of the motion and what defines the end of the motion. So the motion we care about begins when the car goes off the roof. So after, or the cliff. So after the car has left the cliff, the instant the car has left the cliff. And it ends the instant the car hits the ground. Now another way to think of this is it begins when the car is leaving the cliff, and it ends when the car gets to the location in the world of the ground. Because what we want to prevent ourselves from doing is thinking about the actual hitting of the ground, the part of the motion. This is right as it hits the ground. As soon as the ground comes into play, the motion's over. So we don't care how it comes to a stop. We don't care that it gets crimpled. We don't care about any of that stuff. If he drives off like the Dukes of Hazzard, none of that we don't care about. We care about the instant it hits the ground, and then we're done. Okay, so like in our one-dimensional problems, we're going to assess what type of problem this is. Well, as it's flying off a cliff with some initial velocity is given, we know that we're in the case of 2D projectile motion, and I'm going to use those interchangeably. For our purposes, we're only going to look at two-dimensional motion, that's projectile motion. Okay, so he's flying off the cliff. We're dealing with a single object, and you guessed it, we'll eventually get more than one. And we're looking at this behavior. All right, now it's time to draw our picture. So first we can start off with just sort of identifying our situation. Here's the car. It's just driving straight off, so it's moving purely horizontal. We need to make sure we're referencing the world. We're going to deal with positions in our players, so we have to identify those positions. But we want to remember, now that we're in two dimensions, we're identifying the world in a horizontal meridian, left and right, and we're going to identify the world in a vertical axis, up and down. So we have to not set one origin, we have to set two. So we need to set our left and right origin, so everything to the right of wherever it is positive, everything to the left is negative. So let's set our horizontal origin, x horizontal, equal to 0, right at the edge of the cliff, right where the car is when it goes off, in the horizontal world. We also have to set our vertical world. Okay, so just keeping in mind, this means that everything that way is positive, everything that way is negative. So let's set our vertical world. I'm going to use a different color and would encourage you to do so as well, just to differentiate them. I like to set the vertical world at the ground. It doesn't have to be, you can set it wherever you want. That's the beauty of it. But I'm going to set the vertical world, x vertical, equal to 0, right at the ground. So everything above is positive, Everything below is negative. Now, I've chosen to identify my position by x as the generic and have subscripted it to indicate the direction. So x horizontal is the position on the horizontal axis. X vertical is the position on the vertical axis. Sometimes that's given as a y position. That's fine. Sometimes it's given as a z position. It could be given as a banana position for all we care. It's just representing the variable in the vertical direction. So for our purposes, for my purposes, I've chosen the letter x to do that, and I've given a subscript vertical. All right. Now that we have identified the world and our orientation, our coordinate system, it's time to list our known variables. But remember, we have 2 dimensions. We have 2 lists. We have a list that is going to identify the motion horizontally, and we have a list that will identify the motion vertically. And this is the power of independence, the power of 2-dimensional motion being able to be separated into horizontal and vertical, because we're experts at that. We're already really practiced at doing things horizontally, and we're really practiced at doing things vertically. Well, now we just have to do it twice, and it's already something we know how to do. So let's make our list. Just like in the problem solving with 1 dimension, we will have an initial position horizontal. We will have a final position horizontal, an initial velocity horizontal, a final velocity horizontal, a horizontal acceleration, and a horizontal time. And for now, I'm going to keep these variables completely separate, but we might find that some are related to each other. So we have an initial vertical position, a final vertical, an initial vertical velocity, a final vertical velocity, a vertical acceleration, and a vertical time. So let's think about these 2 values and these lists. I want you to think about time for a minute. How does the motion, this is the time of the motion this time, how long the motion takes. How does it change between horizontal and vertical? Are they different? Well, the object can't really travel a different amount of time horizontally than it does vertically. It's one object. So even though it's traveling in 2 dimensions, it's doing it over the same amount of time. So moving forward, I want us to be able to think about that proactively and realize that our times are not dependent on direction, but in fact they're the same, and that's going to be useful for us. We want to keep that in mind, that the time horizontal equals the time vertical. It's the time of the motion, so we're just going to call it t, and now my 2 lists are connected, and that's going to be important for us. Okay, so let's fill in these lists of what we know, what's implied, and then if we can make some predictions about it. So x initial, well, the car is starting in the left and right world. It's starting right at that 0 point. X final, we don't know. I'm sort of checking back to what the problem was telling us. V initial horizontal, how fast is the car moving purely horizontally? Well, it tells us the car is just driving off. So it was moving horizontally. When it hits that ledge, it doesn't shoot off at any kind of angle. It just goes off horizontally. And so the velocity given in the problem of 20 meters per second is actually purely horizontal. Final velocity, well, now we have to remember about acceleration in the horizontal direction in 2-dimensional motion. And you should have read in your book that unless specified, if an object's flying through the air, we learned this in the previous chapter, that only gravity acts on it, and gravity acts in the vertical direction. So, for basic 2-dimensional projectile motion, without any indication, the acceleration horizontally is going to be 0. Nothing is changing the motion horizontally. There's no influence on that motion like there is in the vertical direction with gravity. So the horizontal acceleration is going to be 0 in our projectile motion. And if that's 0, our initial and our final are actually the same. And so we don't see a difference between initial and final velocity. And our time for the whole motion, well, we're not given that. So we're going to leave that as a question mark. What about in the vertical direction? All right, well, vertical, that's our up and down. And we've seen that we've set the origin here at the base of the cliff. So where does the car start? It starts above that base. And specifically, that cliff is 10 meters high, so it starts at 10 meters. Where does it end? Well, it's going to land on the ground. That ground has been defined for us as 0 meters. Our initial velocity. We're just driving straight off. So right at the object leaving the cliff, it has no vertical velocity. It's as if it's being dropped in the vertical direction. And so our initial vertical velocity is 0. What about our final vertical velocity? This is where we often get a mistake in two-dimensional motion. So we want to be very careful about it. We want to keep in mind that this final velocity is the velocity when the object hits the ground, at the location of the ground. The object's still moving when it hits the ground. It's not until the ground starts to play a role does it stop moving. And then we didn't care about that motion. So our final velocity is some value. We don't know what it is, but it is a value. Acceleration, well, in this dimension, only gravity is acting. So we're in a case of free fall, and we know that our acceleration in free fall is 9.8 times meters per second squared, or 9.81 times meters per second squared. And we don't know the time. All right, so let's make some predictions about what these variables might be so that when we get to the evaluation phase, we feel good about it. X final. Well, if the car's headed in the rightward direction, I anticipate it's moving in the right. It is, based on my velocity and the picture that I've drawn. And so it should have a positive non-zero value. Our time is always going to be positive and non-zero. Our final velocity in the vertical direction, well, that we might anticipate to be negative non-zero. We know that the object is going to be accelerating. It's accelerating in the negative direction. It starts out with a 0 velocity, and it's going to be moving down. Moving down, accelerating in the negative direction, it's getting bigger and bigger, and so our velocity should be a negative non-zero. All right, so those are our predicted values. Now, the next step, just like with the other step, it asks how far does the car land from the base of the cliff, from the base. So this distance away. Well, that is related to the final horizontal position. That's what's going to answer my question. So we go after it. Let's start with that. Given x final as a value and an acceleration that's 0, the equation that's going to make sense for us to use is this one, where it tells us x final based on v initial and my acceleration. We know that acceleration is going to go to 0, but let's just follow our process. X final horizontal is equal to x initial, which is 0, plus v initial, which is 20, times t question mark, so I'm going to leave that at t, plus 1/2, 0, times t squared. And this term goes away, and I'm left with a final position that's dependent on time. Okay, that's all right. Let's go after time. Oh, well, I'm not going to be able to get time from the horizontal motion, but here's where this becomes very important. Maybe I can get time from my vertical information. And if I look, I notice that, and I'm going to use orange to determine this time so as to keep my equation separate, that if I use the same relationship, that gives me final position as a function of its initial position, the initial velocity, and the acceleration. My final position is 0. My initial position is 10. My initial velocity is 0 times time, plus 1/2 negative 9.81 time squared. And I'm able to solve for time. So reducing this equation, I can move 10 to the other side. Minus 10 equals minus 4.9 t squared. Divide both sides by 4.9 and take the square root, and I find that time is equal to 1.43 seconds. So my time, which I used vertical information to get, is the same time as is happening in the horizontal direction. It's the same object. So now I can use that in my relationship. So x final is 20 times 1.43, which is, which is equal to 28.6 meters. And that's my final position, which is how far I am if my origin was set at the base of the cliff. All right, so the process is the same. I've just doubled it. Instead of a single origin, I have 2. Instead of a single list, I have 2. I often have to find 2 different things, but they're related, these two lists, via that time, and that's important. All right, so there's our two-dimensional kinematic process that I want you to follow to be able to show me your understanding of problem solving in 2 dimensions. Good job.